Welcome once again to RF transceiver design course. We are on module 5. We are discussing about passive components and impedance matching. In last lecture we have seen the all from starting from the transmission line to the impedance matching, and on the Smith chart how can you design impedance matching by using a Smith chart, and how you can plot the Q on the Smith chart that we have discussed. Now, in this lecture we are going to discuss about the inductors and inductors on chip. So, if you see the RF inductor means basically RF circuits. RF circuit is a combination of analog circuits. So, analog circuits combination of capacitor. So, mostly in the mixed signal we use this. Now, RF circuit has an additional component, that is the inductors, because in all the RF circuits we are going to use inductors or tuned circuits. So, inductors is a very important and which differentiate the RF circuits compared to the mixed signal circuit, where there is a more analog circuits plus capacitors. So, in analog and digital IC course, you already have seen a NMOS, PMOS, MOS capacitors, resistor and MIM capacitor. So, this is we are already going to use, but in addition there is a inductors that are important for this course. Now, there are various components that we are going to make: low noise amplifier, mixers, voltage control oscillator, power amplifier. In everything we require the passive inductors. And if you have seen in the last 2-3 class, we are discussing about the impedance matching, where inductor plays a crucial role in the impedance matching. So, it is very important to understand the inductors and how you can use the inductors on chip. So, there are if we try to see the theory behind the inductor, what is the inductance L? So, inductance L is given by the amount of flux generated per unit current that is passing through the coil. So, if we have a coil like structure, if you have a coil like structure like this is a coil like structure, and if the current will pass through this unit current I, it will generate the magnetic flux, and that by current will give you the inductance. And if we write a specific about this, it is a mu naught n square pi a square by length. So, here you have a number of turns and what is the area and length. So, your inductance is proportional to the number of turns, area and length. So, here if we see your inductor is proportional to number of turns, area and inversely proportional to the length. Here means mostly the inductors we use, means it is also mentioned as a how much energy stored. So, electrical energy in the form of magnetic energy, that is a inductor. Now, we try to realize this inductor on chip. So, when we try to realize inductor on chip, we will take advantage of the skin effect. So, we all know what is a skin effect, it is already covered in prerequisite electromagnetic theory. So, the at high frequency your current will only travel on the surface, and due to that there is a only means the penetration of the current is 1 by epsilon. So, that uh, skin effect and skin depth. So, the depth at which it will penetrate, it is given by a skin depth. It can be written as a delta which is equal to 2 by omega mu sigma, and we can write the resistivity which is equal to rho L by A. So, as we because of the skin effect, the effective area is reducing, and that will increase the resistance. But because of skin effect, we can also use the very thin layer of the conductor to do the layout of inductor. So, we can give means we can take some specific example which metal widely used in the uh, whatever metal that we are using in semiconductor or semiconductor technologies, that is given by aluminum has a delta which is a 1 point aluminum which is a delta 1.82 micrometer, and copper is also widely used, it is a delta. So, here we are taking a example of skin effect. So, in skin effect, if we consider the frequency of 2 gigahertz, then if we take aluminum, it is around 1.82 micrometer, copper it is 1.48 micrometer. So, that is the skin depth, and if it is cooled, it is 1.76 micrometer. So, this will help us to consider the very thin metal layers in order to trace it out the inductor. So, now we will see that what are the different types of inductor that we can use for our RF transceiver design. So, there are two types of inductors widely used on IC, that is the bond wires and spiral inductors. So, if we see the bond wires, this example I have already given in the first class. So, where we have discussed one of the chip made by Fraunhofer at 220 gigahertz. So, here in this there is a bond wire from pad to the pin. So, through to the package to make the connection to the package. So, this bond wire has a some inductance, and that inductance you can use for the consideration in the when you are designing the circuits. So, we will see the attributes of the bond wires. So, generally it is the diameter of bond wire is the 25 micrometer of diameter. It has a low resistivity compared to the spiral inductor, and it can provide a high Q, the quality factor high. We already have seen the quality factor Q, and it is more than greater than 20 for 1 to 10 gigahertz frequency. So, as a thumb rule, we can consider it as a thumb rule. It is have a 1 nanohenry of inductance per millimeter wave length. So, there are some equations which will came to the equation, and from the experiment this thumb rule has been considered. So, when you are designing, you can keep this in your mind, and it is based on the modeling data. So, but the problem with this bond wire inductance, it is a large variations around 20%. So, we cannot have accuracy in terms of inductance value, then because you can see that at different place the length of the bond wire is different. If you have a, if you want to take it into the corner, it has a different bond wire length, and if you going to use in the middle, it has a different bond wire length. So the variation is 20 percentage. So you cannot estimate the accurate value of the inductance, and you need to do the various chip fabrication in order to come to the final value, and it might shift your frequency of operation, and your impedance matching might mistune to the other frequency. So, this is about the bond wires. Now, we will go for the spiral inductors. So, spiral inductors, it is same analogy. So, in solenoid we are making the wire on the solenoid, we are just making wrap on the solenoid. Here you are doing on the single surface, and that is make a drawn like this. So, this is a one example of the spiral inductor. So, it has a metal traces laid out in form of spiral. We can use any metal, aluminum or copper, or the combination of any metal which is used in the semiconductor technology. But this metal has a as we have discussed, it has a high resistivity, and which because of that the inductor quality factor is reduced. So, aluminum it is 50 milliohm per square meter, and for copper it is 25. So, copper is much better. So, in some of the foundry you can also where it is mostly dedicated RF foundry, mostly IHP BiCMOS process, you can also go for the copper, for the top layer copper material, and it will help you to realize better Q inductors, and the quality factor Q is less than 10 on chip. And it is always, because we generally for frequency greater than 10 gigahertz, the modeling needs to be done. Modeling of inductors should be accurate. Even less than 10 gigahertz, because nowadays all the foundry are providing inductors. We modeled less than 10 gigahertz of frequency, but all these inductors which are provided by foundry are no longer modeled beyond the 10 gigahertz of frequency. So, you need to be careful while choosing the inductors in your foundry. And if you are going for high frequency, let us say very high frequency millimeter wave or sub terahertz, if you are designing a circuit, then a simple conductor can also act as an inductor, and that is a distributed inductor. So, you can also use a distributed transmission line as an inductor. So, if we see this spiral inductor, the important parameters is this uh, width of the traces that we are making, the inner diameter which is given by DEIN, inner diameter, outer diameter which is so this is a D out is the outer diameter, this is a inner diameter, this is the width of the trace, this is a space between two, between two spirals. So, this is the spiral inductor and it is widely used in RF circuits or on chip circuits. These are the attributes of the spiral inductor. Now, if we see the what are the high frequency effect which is coming in the spiral inductor. So, that is important because we are going to use all these inductors at high frequency. So, at high frequency there are, so we can make a circular spiral like this and then there is another spiral which is a square spiral. So, this is a square spiral. So, same thing, all the parameters, the width, space, inner diameter and outer diameter will look like this. So, what are the high frequency effect? So, one of the problem at high frequency is there is a age effect. So, in order to, if there is a edge, and we all know from microcircuit, if there is a edge then there is a possibility of the radiation and that we need to reduce or it will add the more losses. So, how we can change this edge by just using the meandering line. So, instead of directly using the edge, it is better to use a meandering line at each place. So, instead of a square means exact edge, we should use a meandering line at each edge and it will so at high frequency we should avoid the edge and it lowers the Q. Quality factor Q. What is the another effect? That is a substrate loss. So, what are the type of substrate loss? So, one is a dielectric loss because we are going to use a dielectric alpha D, because your silicon is in this case is a dielectric and there are various SiO2 layers. So, that if we see the metal stack of the CMOS process or BiCMOS any process, there are many dielectrics and that will have a, and silicon also has a loss. So, alpha D is a dielectric loss. There is another loss, that is a eddy current loss. So, what is the eddy current? So, when there is a electric, the means when there is a two, if I will try to draw it here. If there are two metal traces, only two has been shown here, and if the current is flowing in this direction, there is a magnetic field. So, this because of the magnetic field and there is a ground here at bottom, there is a eddy current will, because this there is a electric field and around that there is a, so due to the change in the magnetic field, there is a eddy current which will flow in this direction. This is a eddy current and that is happening due to the substrate, and this is a substrate injection that is happening. and because of that this eddy current will also add the loss. And if you plot the eddy current with uh, the loss in the eddy current, loss due to eddy current with frequency, and this is, if this is a loss, it is kind of increasing with the frequency. So, there is a eddy current loss that is important, and that is a current because of the let us say if we consider the solenoid, and if there is a magnetic field, if it will come closer in the proximity to the substrate. However, here there is already the substrate below, and that will start generating the current. That magnetic field which is start generating the current, that is a eddy current. Another loss, that is a hysteresis loss. So, another loss, that is a hysteresis loss. So, this is happening due to the magnetization when we are doing magnetization and demagnetization. And demagnetization, the hysteresis loss will happen. So, hysteresis loss is mostly characterized as the time delay of magnetization vector. So, if we try to draw, so here if we try to draw the magnetization vector, so this is a flux density B versus magnetization force. So, as you start increasing, it is going to use this path. So, this mostly this curve will look like this, and so this is when you start increasing, it is going to use this path, and then means this is increasing, and then it will when you start reducing the magnetic force, then it will use this path. And because of this change, means the difference when you are increasing the magnetization force and the flux density it is increasing, but when it is discharging, so when you are charging and when there is a discharge, at that time it is going to use a another path, and because of that there is a loss, and this loss will be converted in terms of heat, and that is called a hysteresis loss. So, these are the three important laws. So, if we summarize, there is a age effect and there is a substrate losses. What are the three substrate losses? Alpha D dielectric loss, then there is a eddy current loss, and there is a hysteresis loss. So, if you try to plot the loss versus frequency, so this hysteresis loss is almost a constant, and this eddy current loss will increase with the frequency. Same same with the dielectric loss as well. So, this is a high frequency effect, and because of that our quality factor Q of the inductors is reducing. So, common geometry of spiral inductor. So, this is a square geometry, but mostly it is because there is a edge we should avoid this. So, either hexagonal. So, this hexagonal is used, or octagonal. So, this is a octagonal shape, and circular. Circular is much better, but when due to the limitation in lithography, mostly this and this is widely used in the semiconductor technologies. So, these are two spiral inductor which are widely used. So, this is about the spiral inductor. Now, if we want to model the spiral inductor, so here in this case you have a, because there is a distributed the structure is distributed, there is a resistance is distributed across, and and there is a capacitor. So, if there is a inner conductor and outer conductor, so there is a capacitor between, if we have a, if there is a connection here which is made from the another metal layer, and this there is a connection here. So, this generally the connection will be near to each other. So, for this example we can take this as an example, and there is a capacitor between these two. So, and capacitor is also distributed with the substrate. So, it is distributed throughout the your inductor. So, if you try to model, this is a inductance Ls, the series resistance Rs, and this is a coupling capacitor Cs between two P1, means this is, if this is a P1 and if this is a P2, then this is a connection 1 and 2, there is a capacitance Cs. Now, because there are many oxide layers in the substrate, so because of these oxide layers there is a capacitor. So, these are the capacitor, oxide layer capacitor, and there is a resistance which is due to the substrate resistance and substrate capacitance, that is also will be there in the model. So, this is widely known as a pi model of inductor, pi model of inductor. So, we can use either lumped element method or microstrip coupled line method to find out. So, mostly in RF when we are working at very high frequency, we try to use a microstrip coupled line method also, and we trace it out in the EM simulator, the inductor, and find out the more EM effect, and it will help us to model the inductor. And this is a lumped element method which is also used in the circuit models provided by the foundry. So, thank you. We will discuss more about the inductors and transformer in the next class.